Okay, welcome back. So, as I said, this section we're going to talk about some of what we call the periodic trends in properties for elements. And now that we have some idea of understanding this idea of electrons and electron configurations, these periodic trends will make a little more sense. But before we get into the trends themselves, let's look at some general ideas about how we think about these electrons. So, one of the first things to understand is that the electrons in an electron configuration, we can sort of divide into two parts. We have what are called the valence electrons, and these are the electrons in the outermost principal energy level. So, in other words, these are the electrons in all of the orbitals that have the highest n number. So, for example, nitrogen has an electron configuration of 1s2, 2p6, whoops, sorry, let me write this down, sorry, 2p3, so it's 2s2, 2p3, so since 2 is the highest principal quantum number, all of the electrons in any of the orbitals in the second energy level, or the second principal energy level, would be the valence electrons. So the 2s2 and the 2p3, or the 5 valence electrons here. Now, the remaining electrons are what we call the core electrons, right? These are the electrons in any of the lower energy levels. And the reason we make this distinction is that the valence electrons are the more important electrons. These are the electrons that are going to be involved in reactions, are going to be involved in creating ions, are going to be involved in bonding, etc. The core electrons are very stable, very close to the nucleus. They are not going to be involved in any of these kinds of activities. So, we see nitrogen has 5 valence electrons. If we look at a couple of other ones, if let's say we're doing a transition metal like iron here, its electron configuration would be argon 4s2, 3d6. Now, for the transition elements, while the 4s2 are definitely valence electrons, we typically would include these outer d electrons in there as well, since they're currently being filled. So typically, we would include both of these in the valence electrons. And so iron, we would say, would have 8 valence electrons. And all of the lower electrons would be core, right? Now, we can do this with ions as well. So if we have something like aluminum 3+, which has the following 1s2, 2s2, 2p6, right? So 10 electrons, aluminum being 13, losing 3, go back to 10. So it's like neon. So again, these would be the valence electrons, and we'd have 8 valence electrons here, the 2s2, the 2p6. Now, what are some of the things that we can know about this? Well, first of all, an easy way to remember the number of valence electrons in the main group elements, not the transition elements, but the main group. So the first 2 columns and the last 6 columns is that the number of valence electrons will be equal to the group number. So group 1, the alkali metals, has 1 valence electrons, right? It's going to be 1s1. The alkali earth metals have 2 valence electrons. This is going to be s2. And then groups 3 through 8 are going to have 3, 4, 5, 6, 7, and 8 electrons, valence electrons. So we got nitrogen here, right? It's in group 5. We see that it has 5 valence electrons. Aluminum 3+, right, which lost 3 electrons and ended up at neon. Neon's in group 8, right? 8 valence electrons, the noble gases. And so this is a really nice, easy way to remember. So if somebody asks you how many valence electrons chlorine has, you look at chlorine, it's in group 7, it's going to have 7 valence electrons. Right? And that's going to be in an S2P5 setup. That's where those 7 electrons are going to come from. So understanding valence electrons and being able to determine how many, important idea here. Now, we've already talked a little bit about transition metals, and I mentioned in the last section that when these lose electrons, they always lose the s electrons first. Then they lose the d. So if we did on the last slide, if I were to become F2 minus, for example, or let's do F3. Let's do Fe3 plus. So the first two electrons I'm going to lose are the S. So I'm going to lose these 4s electrons. So once I've done that, then I still have to lose one more. So then I'm going to start taking the D. So these are going to be argon. Now, I could write 4 as 0, but I'm just going to, since it's not there, it's going to be 3d5, right? And that would be the 23 electrons. That would be an iron 3 plus. Now, one thing that we can also do from looking at these electron configurations, and probably more usefully the orbital diagrams, is determine whether a species is what we call diamagnetic or paramagnetic. And what this essentially means is that diamagnetic means that all the paired electrons, and so no magnetic field, right? It's not, there's no unpaired charges or unpaired electrons. So something like aluminum 3 plus, right? If we draw out the orbital diagram where we have 2s2, 2p6, where all of these electrons are all paired, this would be diamagnetic. Now, paramagnetic means we have unpaired electrons. And a species with unpaired electrons will have a net magnetic field, so it'll interact with other magnetic fields. And so something like iron, right, which you draw out the orbital diagram, right, the S is filled, but the D, right, we have 6. So 1, 2, 3, 4, 5, 6. So we have these unpaired electrons here. We create a paramagnetic species. And so by looking at the orbital diagram, we can determine whether a species, whether it's an element or an ion, is going to be either diamagnetic or paramagnetic. So dia, all paired, para has unpaired electrons. Okay. So if we look at the whole periodic table, right, we get this sort of idea of valence electrons. And when we start to look at these trends, we're going to look at trends in a couple different ways. We're going to look at trends going across a period. And so if we think generally, what happens as you go across a period is you add protons. Now, as you add protons, you also add electrons. So as you go across, you're adding electrons to an S block, a P block, etc. So you're adding electrons to some energy level, whether it's the second energy level, the third energy level, etc. As you go down, right, now you look at the valence electrons are getting further and further away from the nucleus, right? So your valence electrons go from being the second energy level to the third energy level to the fourth energy level, etc. So we're going to look at trends going across and trends going down. Now, why do we do this? So first of all, if we think back to Mendelev's periodic law, right? This allowed us to predict the properties of the element will be based on where their position is in the periodic table. But it doesn't explain why the pattern is there, right? It just tells us the pattern, right? Mendeleev said, we see this pattern, right? It repeats, right? And so every certain element, every certain number of elements, we get an element that has similar properties, okay? What quantum mechanics is striving to do is to explain why we see this. Why do we see this movement in the properties? Why do we see the size of the atoms change as we go in one direction or another? Or why do we see this property move in one direction as we go across the periodic table? Right? So it tries to explain why we see these periodic trends. So, as I said, a lot of these are based on the electron configuration, and maybe even more importantly, the number of valence electrons. So as we look at these different columns, whether it be, the halogens or the noble gases or the alkali metals, alkalinors, you start to notice patterns, right? Their valence electrons always have the same pattern. So all of the halogens are always S2P5. This is just what energy level you're in. All of the alkali metals are always S1. All of the alkali earth metals are always S2. So the idea is having the same valence electron configuration leads to similar properties. Right? So if you have the same setup of your outer electrons, not surprisingly that maybe those elements are going to behave in similar ways. So we see elements in the same column have similar properties because they have the same number and pattern of valence electrons. As we go across a period, right, of course, they don't have the same properties, but the properties show a way that they pattern in how they change, right? So they change in a predictable way. At least certain properties do. And the quantum mechanical model gives the explanation, again, is based on this idea of valence electrons and the number and the pattern of these valence electrons. Now, one thing that we're going to refer to in several of these periodic trends is this concept of effective nuclear charge. So the nuclear charge is the charge in the nucleus. So let's say we have a nucleus like this one, which is lithium, right? Has a nuclear charge of positive 3 protons. Now, the electrons around the nucleus, right, are attracted, right? Those negative electrons are feeling the pull of that positive charge, right? That opposites attract. But do all of the electrons feel the pull in the same way? Well, the answer is no, right? Electrons that are closer to the nucleus are going to feel what we might say is the full nuclear charge. But as electrons get further and further away, they feel less and less of the nuclear charge. They are what we call shielded from the full nuclear charge effect. And so the idea is these core electrons, so the inner core electrons shield the outer valence electrons from the nuclear charge. And so these valence, these outer electrons, experience what we call an effective nuclear charge. And the way Z effective is calculated is that we take the full nuclear charge, which is Z minus a shielding effect. Now, while it's by no means exact, we can estimate the shielding effect as sort of the number of inner electrons. So, for example, if I wanted to estimate the shielding effect or the effective nuclear charge that this electron feels, I would say that we have the nuclear charge Z of 3 plus. We have 2 inner electrons, the 1s electrons, so 3 minus 2. So that outer electron is feeling an effective nuclear charge of a positive 1, right? So it's attracted to the nucleus, but it's only attracted as if the nucleus had a positive 1 charge instead of a positive 3. So changes in this effective charge are going to have an effect on the properties, how easy it is to lose an electron, how tightly those electrons are held, right? The bigger the charge, the more tightly held those electrons are. So changing Z effective will have an effect on the properties. Okay, so we're going to mention this as we go through a couple of these different properties. So the first trend I want to talk about is probably the most basic of all, and that's just simple atomic size. So how big are the elements? So again, as we go across, we're going to go these two ways. So as we go across, what we see is a decreasing radius of the atoms. So as we go across, now I should point out that all of these trends are going to be based primarily on the main group elements. So we're going to look at the first two columns and the last six. While we may look at these, frankly, a lot of these trends don't really hold up in the transition metals, and so we don't really include them in most of our periodic trends. We just look at the main group elements. So what we see is sort of a steady decrease in size as we go from left to right across. So we go from lithium at 152 all the way to neon at 70, and etc. So and we can see this repeating pattern. As we go across, we see the size gradually decrease. Now, why might that happen? Well, think about what you're doing. So as you go across, you're adding electrons, one electron each element, but you're adding it into the same valence shell. So adding electrons into the same shell doesn't increase shielding. So if we're thinking about Z effective, right, equals Z minus S, if S is relatively constant, so as you go across, Z is increasing because you're adding protons, S is staying the same, so your Z effective gets bigger as you go across, which means those valence electrons are going to be held tighter and tighter, which means they're going to be pulled in, sucked into the nucleus a little bit more, making the atom a little bit smaller. So that's how we can explain why the size of the atoms gets smaller as you go across. How about going down? Well, maybe this is a little bit easier to understand. Not surprising, atoms get bigger as you go down. And this is simply because the valence electrons are further from the nucleus, right? They're in a larger principal energy level. So as you go from having them in, say, the 2p and the 3p and the 4p, right, those electrons are further away from the nucleus, meaning the atom has to be bigger to accommodate those further electrons, or those electrons that are further away. And of course, the Z effective is getting smaller because those electrons are further away. There's more inner electrons that provide more shielding, and so those outer electrons are less and less attracted, which even cause them to expand a little bit more. And so we see the size get a little bit bigger, get bigger as you go down. Now, as I said, transition metals don't really follow these trends. If you look at them, essentially you do see a little bit of decrease, but if you, especially in the middle of these, you really see very little change, right? So in all practicality, you see very similar properties, a very similar size for a lot of the transition metals across a period. So not a whole lot of activity going on there. So that's basic atomic radius. Now what about atomic size? What about ionic size? Okay, so let's talk about ionic radius. So we talked about atomic radius, so neutral atoms, but what about ionic radius? Well, there's a couple of things to think about here. Are we talking about positive ions or negative ions? So let's look at positive ions. So the first thing to understand is that positive ions or cations are always smaller than the neutral atom. So by taking away an electron, by taking away valence electrons, right, you're removing those outer electrons, and your new outer electrons in your ion are going to be closer to the nucleus. And so your positive ions are going to be smaller than the neutral atoms that they came from. If you look at anions or negative ions, anions are always going to be bigger than the neutral atom, right? Because you're adding electrons. So you're going to be adding those electrons and forming that negative ion, and that negative ion is going to be larger than your neutral atom. Okay. So that's the first two basic ideas. Positive ions are always smaller, negative ions are always bigger. Now, one thing you might say that the anions, the negative ions, that, okay, well, but you're adding it to the same level, right? You're just, if you go from O to O2 minus, you're just adding more electrons into that 2p. Why is it bigger? Well, the thing that you're doing is you're not changing. It's not like moving across like you do in our size trend, because you're not adding any more protons. So you're keeping the Z the same, but you're adding more electrons. Those electrons don't like each other, right? As you keep adding more and more electrons, they need to spread out within that energy level. And by doing that, they spread out by sort of spacing them out, which makes the atom get a little bit bigger, right? So simple as that. Those added electrons need to space out so that they're, because of the repulsions with the other electrons. Okay, so what about if you look at trends going up and down, right? So we'll look at positive ions first. And the basic idea is that the trend is essentially the same as what we see in the neutral atoms. So as you go across, the positive ions get smaller and smaller, right? So as you go from lithium to beryllium 2+ to boron 3+, that gets smaller and smaller. So the bigger the positive charge, the smaller the cation is going to be. As you go down, the ions get bigger. So sodium +1 is bigger than lithium, potassium is bigger, and, not surprisingly, as the atoms get bigger, the ions are also going to be bigger as you go down. Okay. So ions increase down the column. Larger positive charge equals smaller cation, right? Larger negative charge, though, let's look at the negative ions. Again, going down, they get bigger, just like the atoms. But unlike the positive ions, as you go across, say, from group 6 to group 7, your negative ions actually get smaller, just like we see with the positive ions. So you go from a -2 oxygen to a -1 fluorine, right? You get a little smaller. So larger negative charge is actually bigger than the smaller negative charge. So if you go all the way across, right, you think about the positive ions getting smaller, and then the negative ions also get smaller. But the difference is the positive ions are getting more positive, the negative ions are getting less negative. So you're gaining less electrons. Okay. So that's your basic trend. Now, you got to be really careful when you compare ions like this, right? We can really only compare what we call isoelectronic species. So what are isoelectronic species, right? Simply means same number of electrons. So what's an example of an isoelectronic series? Well, that would be something like let's look at sodium +1. So let's go magnesium. Well, we can go all the way. Aluminum 3+, magnesium 2+, sodium +, right? All have 10 electrons. Right? What else is going to have 10 electrons? Well, F-, O2-. Right? All of these ions are isoelectronic. They all have 10 electrons. And if you're comparing an isoelectronic series, the biggest positive charge is going to be the smallest. The biggest negative charge is going to be the largest. So if you look over here, aluminum 3 plus is about 50. And if you look at O2 minus, find it on the table here, it's about 140. So biggest positive charge is going to be the smallest ion. The biggest negative charge in the series is going to be the largest ion. So that's sort of the general ideas behind ions. So we can look at sort of within a group of positive ions or a group of negative ions, or we can look sort of more globally at isoelectronic series.